take in. And so I'm going to show you the first time these DRCs and see if you can pick anything out. The second time I'm going to annotate it, and then you'll see it for sure. So these are all DRCs. Okay, so now we're going to annotate it. So there's a lot of information. The radar operator has to really focus on what's happening in one area and then load shed everything else, because if they don't, they're not going to be able to see what they need to see. So there's all 6 cell mergers right there. So what happens with a cell merger is you generally get an enhancement of the precipitation. So when 2 storms come together, the reflectivity will increase where the merger takes place. Now we see the DRC for each one. The top is a very small core, and the Chillicothe one maybe is the largest of the cores. Then you can see that they're all more lined up now. You can kind of see what they kind of look like, this wedge shape a little bit. There's a concaveness to some of them. We often see that. This one here is a lower reflectivity DRC. We go back one, see where the cell merger here is a little bit lower reflectivity. And then when the DRC for these cases reaches the ground, in every case, the tornado forms. And so we found that the leading edge, actually the core of the DRC will reach the ground anywhere from near the tornado start time to about 4 minutes in advance. So we have about a 4-minute variance. And so all 6 of these cases had cell mergers. The most obvious ones were the first 5. So if you go back and see, you can see these cells, they all merge there. What about this one here? All right, so you've heard about Cameron Nixon. When he got to the SBC, he said, yeah, great study, Chris, I love it. But the Windsor storm doesn't seem to have a DRC, and it doesn't seem to have a cell merger. And he confronted me. I told him, I said, well, I don't want to give you an answer. Let me go back and look at the data, and I'll see what I find. So, if you look here, there's not really a whole lot here, but I've marked where the cell, I think, is. But if you look at the cross-section, we're going to see something profound. That's where the cross-section is. So it's a relatively weak reflectivity. We're all the way in eastern Colorado here. But what happened on this day? First of all, I wanted to show to Cameron that this was the only DRC along this cross-section that happened. So that gives us the timing that we need to anticipate the tornado. And then second of all, I zoomed it back out just to make sure that there weren't any other DRCs. What I noticed was that there was a weak reflectivity cell that developed about 10 miles to the southwest, to the south of the storm. And it grew, and it was just a cell. It wasn't anything that you might notice, really, unless you were really paying attention. Well, this cell actually moved toward the flanking line of the Windsor storm and then merged. And when it merged, there was a flare-up within the flanking line itself, and there was a big reflectivity enhancement that descended until the tornado formed. So when I showed Cameron this, he looked at me and he said, beautiful. And since then we've been teamed up. We're actually trying to do some research together. This actually is really a fascinating case because this storm that cell there has nothing to do with what's going on with the supercell. And it doesn't look that significant, but yet it's timed in well with the tornado. Now, what if that cell hadn't merged in just at that time? Perhaps the tornado may not have formed at that time, but we don't know. Maybe there would have been a delay. So when we look at this tornado, it was a very legitimate tornado. You know, the reflectivity looked kind of on the low side. But when you look at the actual tornado itself, it was very intense. And you might expect this to be a very high reflectivity large supercell. Well, not necessarily. So when we look at the locations of where the DRC formed relative to the RFD boundary, we see that there was a very reasonable variance in the distribution. And when we actually contour it, we see the maximum value averaged about 0.4 nautical miles to the southwest of the tornado start location. With the study that was done for the Broyles EF4 tornado, they actually found their rear flank downdraft surge, the internal rear flank downdraft surge, which is another word for DRC, was to the southwest of the tornado. Very similar to the average location within our 208 case database. And so if you draw the axis of where high incidence occurred, again, it's to the south of the tornado, but it all depends on how the storm is oriented. In this graphic here, if you want to know more about this graphic, you can read the Tornadogenesis papers. What you need to understand about this graphic is that the data showed that the DRC progressed from southwest to northeast across this distribution, and that the maximum occurrence was 0.4 miles to the southwest of the tornado at the start time. Why is that significant? Because when we calculated the average diameters of all the DRCs, the average diameter of the DRC was 0.41 nautical miles. So what does that say? It says that the leading edge of the DRC moved past the surface circulation seconds before the tornado start time for the average of the 208 storms. That was the most profound moment when I saw. I was just like, wow, this is amazing. And so some people have said, you know, it was a good idea to do the averages of the 208 storms because it tells you a lot when you look at the averages. Now, this is a schematic that was done after we learned this. So we have the DRC coming in. The core remains to the south of the tornado, but the leading edge starts to go around the circulation. The tornado forms and the strongest winds, and then the tornado becomes rapidly stronger. And so this is what it would look like. It's descending, hits the ground, the leading edge comes around the circulation, tornado forms. And so that's where we've marked the DRC based on this graphic here. Let's look at another case. This is the New Orleans, East Louisiana EF3 tornado from 2017. In this case, the cell mergers occurred to the southwest of the storm, but we've lined it up here along the higher reflectivity component within the pendant and the hook. And so when we annotate it, we see that there was a cell there. It's not very prominent, is it? There's two cells there, and then the first one merges, and we see the DRC initiate in the cross section. Just gonna take a look at. But then look here at our graphic and look at the core and how the shape of it and where the RF occlusion is. It looks pretty similar. And then we can see that the DRC nose wraps around the circulation and the tornado begins. The core appears to be south of the tornado, very similar to our graphic. So this case here is the third case. And again, it was like the previous case, the Salyersville case. The tornado was more to the left of the front part of the DRC. And so this is the New Orleans, East Louisiana cross section. We see that cell there. Remember we saw the cell mergers? See, the cell grows, but it actually merges pretty quickly in this cross section. And you see this river here. Why is it jumping around? Because when we did the original study, we kept the cross section exactly on its line. But in this case, I didn't publish it or anything. So I found that the DRC can jump around a little bit from north to south, and just like a supercell, like the core of a supercell can jump around. It's like, oh, it should stay there. No, it jumps around. So what I did was I moved the cross section, maybe up to a quarter mile to try to find where the best reflectivity was. Anyway, there's the cell merger. Again, classic DRC shape. And then it just drops. So this one was actually quick. This DRC developed, and then 3 scans, it dropped to the ground, and the tornado started. And so do we see anything on the velocity? Well, this one shows up pretty good on the velocity. There's the DRC initiating. And we see the velocity there in red. That's a differing speed direction. And then that drops. So you see the DRC actually drops from about 10,000 feet down to the ground. But then also notice that the wind speeds extend pretty high up. And so we're finding that the DRC needs to be a little bit deeper. We'll talk about that in a moment. But let's look at some observations. This happened to be a storm that I saw on May 4th, 2022. I was on a midnight shift, and I got up at 1 in the afternoon, drove down to east of Lubbock. I work at midnight. It was crazy. I was like, as soon as I saw it, I had to turn around and go. But I was about 50 yards from the beginning of this tornado, and I saw the DRC come down visually. I marked it, and when it came down, this big plume of dust went like that, and then I could see dust coming down around the RFD occlusion, and I could see this little ball beginning where the tornado was starting near the ground, and I was just looking at it in awe. So as soon as I got this, I was like, okay, gotta go back to work. It did produce a bunch of tornadoes later on that I missed, but.
And you were how far away?
I was on the back side of it, actually. I was looking east there, so I wasn't in any danger at all.
Okay.
Yeah. But I'm going to show an example of what to do and what not to do shortly. This is what you should do. This is 2.8 miles away from a developing violent tornado in Moore, Oklahoma. I'm on I-35. I'm looking to the northwest, and you can see the tornado here. Let me start the. Okay, this is a time lapse that I put together. Watch when the tornado becomes obscured. Right there, do you see that? That's the DRC moving past. It was absorbed, and then now the EF5 damage is being realized right then. So if I can just move this back. Watch, it's hard to see. All right, so you see the DRC right there? It obscures the tornado. Now, going forward, okay, the tornado is obscured, and now it's absorbed, and then EF5 damage right there. That's when it hit Breyer Elementary School, and it was very, very somber watching this happen, because you know that's in a very populated area. And then when we did the study on the radar, we found that the DRC went around the tornadic circulation, caused the tornado to sort of be disrupted a little bit, and it expanded in diameter. Once the DRC was absorbed, the tornado got its act together, shrunk rapidly, and F5 damage. So this is actually, I also talked to somebody that had done a formal publication on this using high resolution Doppler radar, and he agreed with me that that's what happened. So now we're going to take a look at the Bennington, Kansas storm. Why was the Bennington, Kansas EF3 such a good storm to observe? Primarily because it remained stationary. Also, it had a lot of precipitation streamers. It had some dust. There's just a lot in the air that can show you all the air motions that were occurring. And these are the video screenshots that Henry sent me from his chase partners in his chase group. They covered the tornado pretty much in all directions. It's really fascinating to study. So this is the one that I used for the paper. Then we're going to take a look at Henry's screenshots next. But this is Brian Barnes, he leads storm chase tours, and you can see the start of the tornado in the upper left. And I've marked where the DRC is with the white outlines there. And when the DRC reached that circulation, that's when the tornado started. But we also, as that DRC wrapped around the tornado, we kept getting these vortices right along the edge of the DRC. So the DRC came down, wrapped around the circulation, and on the inner edge, we were getting these vortices that were developing. So we believe that the DRC is a positive source for vortice generation. And so once we got these vortices, the DRC was absorbed. If you notice, there's no darkness now back over here. The DRC has been completely absorbed, and tornado maintenance is now occurring. The occlusion downdraft, which we're going to look at, is prominent by here. It's more of a permanent feature. We're going to take a look at that. So, if we mark the DRC, over here you can see where those vortices were occurring, a little white circle there. So this is the same one. I didn't know he had it in his presentation. What we're learning is the DRC is just a little bit deeper than what we thought. I've taken off the SVC here, but this was Jeremy's position, and this is the tornado start time. So we're actually just zooming up on that left, upper left. We're just zooming up real close on it here. Now, what about Henry's? Henry told me that his position was unfortunate. He wasn't close to the tornado, pretty far away, but he's looking to the southwest here, and he's got a lot of light behind the developing mesocyclone and later on developing tornado. Let's take a look at it. So this is where the tornado forms. You see it in the left side of the screen there. All right. So now let's look at, see the lighter color here, right there. You see that light color? Watch what happens. You see it? Do you see it darken all of a sudden? And then also you see the cloud base lower at the very same time. Now, I mean, you can really see it's darkened up through that whole area. That's the DRC. And so the DRC stretches from that area, which is where the core was, all the way over toward the circulation that's that appears to be descending, but it's not really. It's just the rotation is just sort of developing downward, but it's not descending really. So then the tornado start time is right there. Now, if you look at to the left, immediate left of the tornado, see the darkening that occurs right there? It almost looks like a little bit of a circle. Well, that is the leading edge of the DRC wrapping around the circulation. And so this is a great DRC observation. And what I thought was really great when I saw it was how the DRC appears right there and the descending part of the cloud starts to form. And so in the Moore study, we looked at this, but here's a closer zoomed up of it. So what Henry got here was very significant. You can see that core, just the darkening right there, and then you really see it. You can really see that. I didn't mark it, but you know, it's pretty evident there.
Plus the bug spots on my windshield.
Yeah, and there's also a turkey or something that scoots across the field. But here's the more animation. And so the DRC are these three lines that are a result of the cell merger, and they're in the flanking line moving down toward the circulation of the ground. So when that reaches the circulation, tornado begins. This is the Moore storm. And this was done in conjunction with the radar. And let's take a look at this one here. Remember I talked about the occlusion downdraft? Well, the DRC is this gray, these three gray lines, and the dark three gray lines are the occlusion downdraft. And so the DRC, we're going to see, well, let's take a close look at it. All right, here's a close look. So we have the DRC here with the light three light gray lines. The occlusion downdraft is a more permanent feature, but it appears to become established when the DRC comes down. And in this case, we see them both coming down together, the funnel dropping. Remember what we saw in Henry's video? The DRC comes down and the bowl is descending as well at the same time. And then it reaches the ground. And so the DRC is absorbed and the occlusion downdraft remains. And so, this brings me to what not to do. This is a police officer in Illinois. He was very close to Rochelle. This is the Rochelle tornado. He was a retired police officer, and he drives up to the tornado, and he says, "Where is it going? I don't know where to how do I go? How do I protect myself? I'm just gonna stay here." Then the next thing he says, "It looks like it's coming right toward me." So he backs up 10 feet. Do not do this. I need the sound. Do we have the sound?
I think it's on. It was for Henry.
Okay.
The things that I will do for insight. The things I will do for insight. This is a tornado, and I cannot tell which way it is going, so I don't know how to get away from it. But it looks like it's coming right towards me.
This is an occlusion downdraft observation. When you see the downward motion when the tornado crosses the road,
Yeah, I'd say it's gonna come right over me.
we're going to see debris and
Let's see
condensation
if I
coming
can
down.
back
Look
up
for
here a
that.
little bit and get under the bridge.
Look just up
Yeah,
the
it's
road
coming right over me.
and to the left of the road, and you're going to see the downward motion of the occlusion downdraft.
I have honestly never been in a tornado before.
So he backs up 10 feet.
Yeah, that ain't gonna protect you.
That's a good one for your group.
Make it worse.
Totally crazy. It's coming right. It is coming right over the top of me. It's a little bit scary. I don't really know what to do except just sit here.
Turn around and hightail it.
Maybe
Look for the downward motion.
Oh my gosh. That's crazy. Crazy, crazy.
Okay, look up the road and just to the left.
Ridiculous.
See the downward motion coming? See it coming down?
Oh, man, it is scary. The truck is, oh my gosh. Holy smokes. Oh no. Yeah, that is completely crazy. The truck feels like it's about to lift up off the ground. Not lying. Oh my gosh.
Wow.
Look at that. I don't know. I'm not getting out to look.
Oh, come
And see
on.
if there's any truck damage later. It actually hit the mirror backwards. Both mirrors backwards. Ugh. And so
It's right behind.
back around or not.
All right, that's not what, you do not want to do that.
No, don't do that.
So, for the Bennington, Kansas tornado, it was a little bit more centered within the DRC. And again, what does the DRC do? It blocks the flow here, so that it must go into a narrow corridor, and then the pressure will drop rapidly behind the DRC. And so the Joplin supercell, we're gonna look at this one last. The Joplin supercell has the cells coming in on the north side of your picture, on the left side of the picture. Look what happens. There's a cell merger right here. The DRC initiates right here. Wraps around the RFD. It wraps around the surface circulation, and the tornado begins. Very fast. And where was the DRC location? Again, pretty well centered on the DRC for this one. So, what I should say is that I didn't mark the positions of the DRC until after the presentation was completely finished. So I didn't cherry pick these cases. I thought, wouldn't it be cool to show where the DRC locations are? So, there we have 6 drawn of the locations. And so, when we look at Ted Fujita's supercell schematic from 1974, he has a tornado centered on a curved area of strong winds, much like what we see in the locations I showed you. And when you read his research, he talks about the descending rain curtains and the descending downdraft to the west of the tornado, coming south of the tornado, and then the tornado developing. He talks about the occlusion downdraft, which we just saw an observation of. So it matches our graphic schematic, which we did not do, and I did not find his schematic until after the project was done. So this was all done in advance. I didn't work off of his work. So we are in agreement. And in 1992, I was working at the National Center for Atmospheric Research as an intern. And somebody came to me and said, Ted Fujita is speaking at the main campus in town. You might want to go and check it out. So I rushed down there. I was like, okay, I'm gonna be like a real reporter. I'm not, but I'm just gonna pose as a reporter, somebody important. And I'm gonna interview him after he's done. And he talked about his damage surveys from April 3rd and 4th, 1974, where he would fly and look down on all the violent tornadoes. There were 30 that day. And he would notice that there was a damage swath often before the tornado began, southwest of the tornado start location, and that it would be a sort of a straight line or maybe a little bit of a curved damage swath. Then you would get the ball of the rotational damage, and then that swath would continue, and then you would get the tornado track. And also, I thought, wouldn't it be cool, since he's talking about and showing his tornado simulator, wouldn't it be cool to develop my own simulator? So I went back home and I'm dreaming about what I'm gonna do. And so I got this grand idea to develop this thing. So this is definitely inspired by Ted Fujita here. And this was the storm as it was 12 years ago in the Whittier Library in Norman, Oklahoma. That is just a cloth tornado. Actually, I put that in there visually. Don't tell anybody. But I did have a cloth tornado actually that looked just like that. And the envelope you can see is very small compared to what I have now. But when I had that in my garage for a long time. My wife 2 years ago told me that I had to move it out to the shed. So that's what it looked like a week ago. And I kept waiting for warmer weather and never got it because it was in the garage and I had to fix this thing up. So my wife said, go ahead, bring it in. It was my fault. And so I added a new vacuum into it. Mouse had chewed the cord of the old one. This is the original tornado bottle that I had made. So that would be the mesocyclone simulator. I added the batting around it. I repaired this. Actually, this is the old version, and that's a newer version there, the ring shaft. And then to make the anvil, I just grabbed a bunch of scraps in the garage and put it all together in the kitchen. And that's the anvil there. It's got some support boards inside of it so it doesn't flop. And so that's it. Now we're going to take a look at the tornado. And